Video 3 ended with a question about ordering. When multiple subgoals are relevant, which ordering constraints are required by the domain, and which are artifacts of the search strategy? In this warehouse, the two deliveries share one robot and one gripper. That shared resource structure makes ordering part of the planning problem, not a post-processing choice. In state space search, the branching happens at the level of action choice. The search commits to one action branch for the red delivery or another action branch for the blue delivery before the dependency structure is explicit. This creates a search control issue. The search may introduce ordering commitments that are not entailed by the domain model, and then duplicate reasoning across multiple branches. Plan space planning addresses this by searching over partial plans. The planner starts from an incomplete plan and applies refinement operations only where the current plan has a flaw. In state space search, a node denotes a world state and an edge denotes action application. In plan space search, a node denotes a partial plan. The partial plan contains actions, ordering constraints, and causal links. The initial partial plan contains two dummy actions, start and finish, together with goal conditions on finish that are not yet supported. These unsupported preconditions are open goals. A second class of flaw is a threat, namely an action that can interfere with a causal link. Search terminates when the partial plan has no flaws. At that point, the plan has consistent support structure and consistent ordering constraints. Consider one open goal. The plan still requires the red box to be in storage A. The refinement question is which action can establish that condition. In this domain, the relevant refinement is the put-down action at storage A. The action is added as a new plan step. The planner does not linearize the full plan. It inserts one step into the current partial plan. A causal link is then added from that step to finish to record that this step establishes the required condition. The new step introduces additional open goals. The robot must arrive at storage A, and the robot must be carrying the red box. The red delivery subplan is constructed by resolving those new open goals. To support carrying the red box, the plan needs a pickup action at the dock. To support the robot being at storage A, the plan needs a move action from the dock to storage A. Each of these additions is recorded through causal links to the later step that consumes the corresponding condition. Some preconditions are already supported by start. The initial state provides the robot at the dock, the red box at the dock, and an empty gripper for the pickup action. The result is a partial plan in which each action has a causal role. The structure is not just a sequence of actions. It is a network of support relations. The next flaw is a threat on one of those causal links. The pickup step relies on the robot remaining at the dock until the pickup occurs. The move to storage A deletes that condition. If the move is ordered too early, the causal support for pickup no longer holds. This is the standard threat pattern in plan space planning. One action can intervene between a provider and a consumer of the same condition. The local repair is to add an ordering constraint that keeps the pickup before the move. This illustrates why plan space planners add order late. The ordering constraint is introduced because of causal interaction, not because the planner committed to a total sequence at the root. Now add the open goal for the blue delivery. The planner must eventually place the blue box in storage B. The blue pickup also depends on the robot being at the dock, the blue box being at the dock, and the gripper being empty. The red subplan consumes two of those conditions. The pickup consumes the empty gripper, and the move to storage A removes the robot from the dock. Those conditions are restored by different actions in the red subplan. The put-down restores the free gripper, and the return move restores the robot at the dock. The resulting cross-delivery ordering is therefore derived by refinement. The blue pickup is not postponed arbitrarily. It is postponed because its support conditions are not available earlier. Now we can state least commitment precisely. Does not mean no order. It means no unjustified order. A total order plan commits to many action positions immediately. Some of those commitments may be correct, but they are not all required at the time they are introduced. Plan space planning instead preserves only the ordering constraints that follow from causal links, threats, and binding decisions. In this warehouse, the final execution is still largely serial because the shared robot creates real dependencies between the two delivery chains. The advantage is that these dependencies were derived from the refinement process. The planner introduced commitment when the model required it, not earlier. The main concepts are now in place. Plan-space search operates on partial plans rather than explicit states. It resolves two classes of flaws: open goals and threats. Open goals require new support. Threats require protection of existing causal links. The plan representation therefore separates action selection from unnecessary total ordering. That representation alone does not determine search control. Once several partial plans or several possible refinements exist, the planner still needs guidance. The next topic is heuristics for planning. The question is how to rank candidate refinements or candidate partial plans so that search effort is directed toward the most informative choices.